Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada. Today is a special event for Computer Science Education Week, and my name is Stacey Joyce. I will be your host. If you're joining us live, make sure that you ask questions anytime throughout the entire webinar. You can do that by clicking the Q&A button at the bottom of your screen. And if you see that someone else has asked a question that you're also wondering about the answer to, then there is a thumbs up icon you can click next to that question, and that'll help me prioritize questions in case we have multiple classes wondering the same thing. If you include your school name, your city, or maybe your teacher's name, something like that, when you ask your question, we'd love to give you a shout out so that you know that was the one that you had asked. Today's guest is Dr. Aaron Langille. He is a master lecturer in computer science and video game design in the Department of Mathematics and Computer Science at Laurentian University. Thank you so much for joining us, Aaron. I will let you take it away.
All right, thank you, Stacey. I'm going to go ahead and share my screen so that everybody can see what we're going to talk about today. Thank you for everybody that's tuning in live and for everybody that's going to view this on the recorded session as well. Welcome. Today we're going to talk about a very early introduction to coding. So we're going to take a look at what we can do with computer code and what computer code sort of does for us, whether it's an everyday application or something a little bit fancier than that. It's kind of important when we're talking about computer code that we start with the hardware. So for anybody listening, hardware is basically all of the things that you can hold. So I've got a few examples here on the screen that I'm sure a lot of people are going to be familiar with. A laptop, a cell phone, an iPad would be similar, or a tablet computer. There's a Switch, a Nintendo Switch, an Xbox would be the same kind of idea, a Game Boy. Any one of these sort of hardware pieces is what makes all of the things that we do on computers and devices possible, but we also have to add the component of software. So the hardware is kind of like a car, and the software is a little bit like the gas. So if we don't have the software, we have a car that really can't go anywhere. Now, the way that we write software, so computer scientists and software developers and anybody that's creating software for any sort of reason has to do it through computer code. Now, it doesn't matter whether or not you're talking about a game. So here I've put up Angry Birds. Hopefully a handful of people are familiar with this one. And there's a few arrows here that show just some of the things that a computer or a tablet or a video game console need to think about, so to speak, in order to make the game happen. So the very first arrow sort of pointing at the yellow bird has to determine how far back we've pulled the bird. And if anybody's played the game, they know that the further back you pull, the faster the bird goes. This particular bird can split into three, so at a certain point where that second arrow is, we have to divide that bird into three pieces so that they can do their work. That last arrow kind of shows that we have to decide, or the computer has to decide rather, how the impact of that bird on the structure is going to cause things to fall over, cause things to break. So the computer has to handle all of these things. So the hardware, the things that we hold, are going to do the calculations, but we have to write the software that tells the hardware what it's going to be looking for. Here's another game that we play in my classes here at Laurentian University sometimes called Overcooked. And again, I would imagine there's a handful of people that are familiar with this one. And the idea here is the same. How do we take our piece of hardware, whatever it happens to be, and teach it or instruct it how to cook the hamburgers or to control the players or to cut the tomatoes or to deliver the prepared food? So all of these things are what computer coders or computer programmers have to manage and have to work on, whether or not they're working in a team or working by themselves. So video games are kind of a really fun way to think about what computer programmers and computer coders are capable of doing when they write software. Some of the maybe less fun, but still very, very important things that we do when we write computer code can be as important as predicting the weather. So when we ask our cell phones, or we ask our home assistants, or we even look on TV to see what the weather is going to do today. A lot of computers are working all the time. They look at what the weather was like yesterday. They look at what the weather was like a month ago. They look at what the weather was like years ago. And they create what's called a model. And a model is kind of a simplified version of the real world. So the code that we write is able to take lots of pieces of information and do what we would call predicting. And that means taking information from the past and trying to decide what's going to happen in the future. And so this is what we do when we're looking at the weather. So when we ask a device of any kind what the temperature is going to be today, and it says it's going to be a certain temperature all day long, then we know that we're getting that from a particular piece of software. And again, this is all done through computer code, which I'll show you in a couple of moments. One of the funner things that's sort of happening right now is self-driving cars, which is kind of neat, because when I was a kid, the closest thing to a self-driving car was little matchbox cars that we would kind of just roll down the hill and hope that they landed where we wanted them to. And now we have cars that actually carry people from one place to another, maybe from your home to the mall or to a restaurant or wherever you need to go, and they do it sort of without you having to have your hands on the steering wheel. So it's kind of fun, it's kind of exciting. And again, the cars themselves are a lot like an iPad. They're the hardware. And what we need to do is we need to teach a vehicle what it looks like to sort of be in the real world, where there are trees and there are other cars and there are people walking. And so our self-driving car has to understand the world around it. And it's a little bit different from the way we do it with our sight and our hearing and our touch. So all of our senses sort of give us a view of the world. But what we need to do is we need to use software, again, computer code, to teach something like a car what it's like to be on a busy street, or even just a quiet street, or even just where we need to go. So again, that falls under computer code. I took a couple of pictures maybe about 10 minutes ago. I would imagine a handful of people have done this before. So the puppy face, or the sunglasses that I don't actually happen to be wearing that have palm trees. Surprisingly, there are no palm trees in my office. But this is done using what we would call an image filter. And so a lot of our phones and devices now have cameras in them. And what we can do is we can actually, through software, through computer code, have our device recognize where our face is. So if anybody's tried one of these before, you know that you can even move your face while these images, while the ears and the nose or the sunglasses are on your face, and it follows you. And again, much like the self-driving car, much like the weather simulation, we do this all by writing instructions for the computer. So I threw this image on just to give you an idea of the complexity that we use as people when we're trying to communicate. So even if you can't read all of the words up there, they all say hello. So if you just look at the colors and you look at the shapes, you can see all different ways to say hello. Maybe you have some people in your class that can say hello in a different language. Maybe you can say hello in a handful of languages. But the idea here is to kind of take a look at how humans interact with each other with different languages, and then to try to understand that computers can do the same thing. So this version, and again, even if you don't know what all of those words are, all the different colors and shapes are just showing you different languages that we use to communicate with computers. Now, some of these languages are a little bit simpler. Some of them are a little bit more complex, but all of the languages are ones that we use to write instructions to make the computer hardware do what we want to do, or to write software. So let's take a look at a fairly simple example, something that computers do really, really well, something that hardware can do very, very quickly is working with mathematics. So we're going to do something, we're going to do what's hopefully the most straightforward version, and that's adding. Now, I don't want to make it too easy. Pardon me. So we're not going to add 1 plus 2 or 2 plus 3. we're going to add some big numbers because we want to make sure that the computer has a little bit of challenge ahead of it. So if I asked you to add these two numbers, I'm sure some people that are watching or listening would say, those numbers are too big. And some people would say, I got that, no problem. And it doesn't matter what your math skills are, because today we're talking about how to make a computer do that work for you. So each one of these numbers one of them's about 500,000, so that's a pretty big number. And the other one's only a little bit smaller than that. So how do we get a computer to actually add those two numbers for us? So what we can do is we can take a look at what they would look like in the language of computers. Now, I don't want you to worry about whether or not you can read everything that's happening on the screen. The point is just to take a look at the differences. So don't worry if it doesn't make sense. For some people, you'll see that we're putting one number into a container called X and another number into a container called Y, and then we're adding them and printing them. And it doesn't really matter what those two numbers add up to in this case. You can do that after the webinar is over. You can work on that problem. But we have one language called Python, which is over on the left. And it's actually fairly simple. It's something that if you had a piece of paper, you could kind of work out yourself. The one on the right, however, is much more complicated. And each one of these languages, all it does is add those two numbers together. And yet, there's a lot of difference. And one of the things to keep in mind if you start learning to code is that a lot of these computer languages are going to feel like the one on the right, even if they act like the one on the left. If anybody's learned to play a musical instrument, or if anybody's learned a second or third language, you know that it can be really complicated at first, but after you practice for a little while, and once you've done a few examples, it starts to make a little bit more sense. So the trick to either one of these, the one on the left or the one on the right, is just practice. Let's take a look at a little example that I would have done when I was probably in grade 1, 2, or 3. So the computer languages from that time ago, it was a little while ago, I don't mind saying that much, were a little bit different. And one of the languages that I was able to use was called Logo. And Logo's job wasn't to write programs that predict the weather. It wasn't to write video games that play on an iPad or an Xbox. It was just to teach you the idea of how we communicate with computers. So since computers are different from us, we need ways to talk to them. So there's a little icon on your screen. Hopefully it's clear. It's actually a little turtle. And what happens is when you use Logo, the item that does the drawing for you is actually called the turtle. So you can take a look at the history of that later on if you're curious. So what we're going to do is we're going to take our turtle and we're going to give it a simple instruction. And one of the things that I teach my students, whether they're in primary grades or high school or university level, is that computers can really only do simple instructions. But what they do is they do those simple instructions really fast and really accurately. So we're going to give our little turtle a very simple instruction to go forward. So inside that blue box, it says to go forward 100. Now 100 is just a distance, so don't worry too much about how far our turtle is going to go. But if we tell our turtle that we'd like the turtle to move forward 100 spaces, we end up with something that looks like this. So there's a fairly simple command, kind of like telling your pet to sit, kind of like asking somebody to pass the salt at the dinner table. We've asked the turtle to move forward 100 spaces. Now, if I issue another command to the turtle, so we talk about commands when we're doing computer coding, I can ask the turtle to turn left. So if we see what happens when the turtle turns left, the turtle simply rotates to the left. So we now have the turtle facing in another direction. And if we ask the turtle to move forward, so if we do what we did before and we say, hey, turtle, move forward 100 spaces again, and I'm gonna hit next here, then we get the starting of a square. So we ask the turtle to move forward, then we ask the turtle to turn, and then we ask the turtle to move forward again. Now, it's surprising how similar what we're doing here to simply draw a square is to the instructions that we could give a computer to write a video game or predict the weather or to look into a self-driving car. We simply have to give it more commands, more instructions that it can compute, again, using its high speed and accuracy. So if we wanted to finish, we could just ask the turtle to turn left, go forward 100, then turn left and go forward 100. So if you're able to kind of trace the screen with your finger, again, the turtle's going to turn left, move forward, turn left, move forward. And when the turtle is done, it's right back to where it started. So what we've managed to do with just a handful of really simple instructions is draw a square. It doesn't seem all that complicated, but everything that's in there form the building blocks of what we would do for more complicated software. So if we move our turtle and square over a little bit, you'll see that these are all the instructions we gave it. Move forward, turn left, move forward, turn left, move forward, turn left. And that turn left at the bottom actually isn't really needed, and our turtle should be facing its original direction, but we won't worry too much about that. What we can do with some of our programs, with some of our computer code, is we strive to make it a little bit shorter. So we want to use things that the computer can handle, and this is something called a loop. Now, what this does is it repeats the same forward 100, then left 4 times. So if you're able to work through those words, we have repeat 4, and then inside those square brackets, we have forward 100 and left. And all that this does is tell the turtle 4 times to move forward and turn left. So we can write what's in that tall bubble in a different way, and we get what's in that short bubble. And all of this is actual computer code in a language called Logo. And Logo is still around. You can play with it. So ask your teacher, ask your parents if they can find a place that you can play with Logo, and you can draw things like this. And I'll issue a little challenge. See if you can draw a 5-point star. It's very similar. You simply have to change a couple of things. So I'll leave that challenge with everybody that's listening today. So the thing that we did with that square, it has a fancy name. Now, before I tell you what the name is, that fancy square is basically, the instructions that we've given it are basically like a recipe. And the recipe, which if you're looking at the image that's on the screen now, this is a recipe for chocolate cake. And I show this to my university students every year. Every year they ask me why there's a hot pepper in it, and every year I'm not quite sure, but that's not really the important part here. There's a lot of wonderful ingredients here. There's butter, there's chocolate, there's flour. You know, change the ingredients to whatever you think that you would like the best when you're looking at this image. But what we have is a recipe. So these are the ingredients, and somewhere, hopefully off to the side on the counter, is a list of instructions on how we're going to use those ingredients. And if we do it right, we end up with something like this at the end. So when we write computer code, even as simple as our little square example, we are writing computer recipes called algorithms. So that's a good word that you can look up later on today or tomorrow or the next time you're interested in thinking about what it's like to design computer code. Look up the word algorithms. And it basically is a computer recipe to get a job done. So if we were to go back a couple of slides and look at those instructions to draw the square, that's an algorithm. And when we take all the pieces like forward and left and those numbers, and then we follow the instructions of doing one after another, we get the computer equivalent of a chocolate cake, which in our case happened to be a square drawn by a turtle. But I think the idea is still there. So with that in mind, and because our time is fairly short today, what can you do to learn to code? How can you start? Well, if you're brand new, and it really doesn't matter how old you are or how young you are, if you're brand new to code, I want you to break it down into really small pieces at first. It can be very frustrating when you start to do tasks that you're not quite ready for. So if you're brand new, I highly recommend checking out the online, I guess it's a game called Lightbot. And what Lightbot does is it introduces you to the idea of writing down instructions that happen one after another. So it might be a little bit hard to see what's happening because these images keep restarting, but the arrows And all of the different icons that are at the bottom are the instructions that the Lightbot has to follow to get to its destination. So what this does is it introduces you to something that programmers would call logic. So before we start worrying about words like forward and left, and before we start worrying about more complicated languages, which we can work on later on, we need to understand what it means to just put some instructions down and to have a computer, or in this case, the Lightbot, follow your instructions. So this is a really great website to try to learn some logic. And I have to thank Stacy for reminding me that this was out there and for sending it to me earlier this morning and saying, hey, why don't we mention this too? Because this is a really good resource for people that are just starting out. If you're at the point where you understand the idea of setting the computer some instructions and you want to move forward a little bit, you can start to get into things like Scratch. Now, Scratch is a programming language that allows you to do computer code without getting into the complexities of the addition example that I showed you earlier. So what Scratch allows you to do is it allows you to use what are called drag and drop colored blocks. So this means that there isn't as much typing as there would be in a more complicated coding language. You can use these colored blocks. Now, there are some things to think about when you're programming with Scratch. You still have to do some logic. You do get the opportunity to work with some images. So if you have an idea for a game, for example, Scratch is a really great place to practice, and it's a really good introductory language that would get you well on your way to doing bigger projects later on. So again, it's called Scratch. It uses a graphical, which just means that you can see what's happening in all the language, and it's a really good resource to start once you've done something like the Lightbot, and once you can sort of handle a little bit more logic, like the apples falling into the bowl in this case. There is a particular publisher that's very good. I'm not trying to plug anybody in particular, but I do want to mention that the publisher No Starch Press has some very reasonably priced books on Scratch. So there's Super Scratch Programming Adventure, Learn to Program with Scratch, and Scratch Junior. So any teachers or parents or guardians or anybody else that's listening that wants to help people get started in coding. And again, this can be done for any age. Scratch is a really, really cool coding environment to get you started, no matter what your level, or sorry, I guess when you're starting, and then it'll help you move on to the next level later on. So those are some resources you can look up. There are also quite a few online tutorials for Scratch. It's very well supported. It has a really, really good community, and it is in use by a number of organizations that do teach both kids and adults how to code. Something else that I was thinking about last night that's very similar to Scratch and sort of gives you a hardware and software. So remember, from the beginning, hardware is the things we can hold, and software is the things that make the hardware move or do what we want it to do. Lego Robotics, so Lego NXT, has a very straightforward programming interface. Now, this does need a little bit of attention and a little bit of care. So I highly recommend that kids and adults team up for this one to build a robot. So you can see the robot kind of dancing around all over the place here on your screen. So if you team up and if you share the building and share the programming, it's very similar to Scratch. And what those colored blocks inside the middle of the non-moving part of the screen are doing is they're controlling the motors. So when you build a Lego NXT robot, you have the opportunity to put a battery in it and to actually have the motors and the sensors that can determine color of light and how much light is being shone on a particular location. You have the opportunity of making all of those things work. And it happens very much like Scratch, where you drag blocks down and put them in place. It's actually very similar to Lightbot as well. So those are three different things you can start at. I know that a number of schools do have NXT kits that are hopefully still in working order and still can be found by people that want to get started with things like this. So that's another option for anybody that wants to get started with a little bit of programming that's very straightforward. Sphero, I haven't had much of an opportunity to play with Sphero. Sphero is really cool where you can control, most of them are sort of ball shaped. There is one that's cylindrical, and you can do two things with Sphero. One, you can control it from a device like a cell phone or an iPad, or two, you can program it and then tell it to go and do a task. So in this case, the ball starts at one end of the table and then makes its way towards the little mini bowling pins and knocks them over. So this is another opportunity to work with some fairly straightforward computer code that both kids and adults could work through some logic and have a lot of fun with. I highly recommend, as you're learning to code, or if you are interested in learning to code, that you do things that are fun. It makes it much, much easier to learn. If you have the opportunity and you want something a little bit more structured, if you want somebody to help you learn the basics of both logic and a particular coding language, check out Canada Learning Code in your area. They have a lot of resources. They run workshops on languages like Scratch. If there are people that are listening that have done a little bit of coding and want to move a little bit further ahead, they do sessions on web programming and all sorts of things. They're a fantastic organization, and I highly recommend looking them up. Kids, have a parent, guardian, or teacher help you with this and see if there are any sessions that are available to go to with your parents, with your guardians, or whether or not a teacher can help set one of those up, because they're a lot of fun and they're really, really good for learning how to code. I'm going to end with my contact information. So anybody that's watching that wants to send me an email, my email address is at the top. Anybody that happens to be on Twitter, that's a fairly good way of getting a hold of me as well. So I'll leave that up there for a couple of seconds. So if anybody wants to jot it down, if you're watching live, and of course it'll be available on the recording afterwards as well.
Well, thank you so much for sharing all of that information with us and giving us a broader context of how coding fits in, not just with video games, but many other applications that those watching may not have thought of. I've had the chance to listen to a similar presentation by Aaron Langille before, so this is my second go around with this. But I guess the first question is, when you talk about games and things like that, like the Angry Bird example with the catapult or the pulling the bird back, letting it go, how does the computer know how to react to whatever it is that the user does?
So it's actually very similar to what we did with the turtle. So the instructions get a little bit more complicated, but the idea is still there. So when you put your, let's assume you're playing on a device like an iPad or an iPhone. The computer will check whether or not you've put your finger on the bird. So much the way that we gave an instruction for the turtle to move forward 100 spaces, we can ask our device, is the user's finger on the yellow bird? And the device will answer back, yes or no. Once we've established that the user's finger is on, or that the player's finger is on the yellow bird, and they start to move backwards, we can say to the computer, we can say, measure how far back they go. So it sounds like it's a little bit more complicated than just moving forward 100, but the idea is very similar. Once we know how far back the user or player has pulled the little yellow bird in the slingshot, then we can start to do math. Now that gets a little bit more complicated, and that's math that a lot of people won't really get to until high school or university. It involves physics and all sorts of wonderful things, all sorts of wonderful mathematics, but it's very, very similar to what we did with our square and our turtle. We simply are asking the computer or the hardware device over and over again, what's happening now? What's the result of what's happening now? And then show me what's happening. So the instructions are surprisingly similar, a little bit more complicated, but the idea is very, very much the same.
Very interesting. Next up, I wanted to ask you, what is the most challenging part of coding?
Well, if you ask 10 people that question, you'd probably get 10 different answers. So I think what I would say is two things. I'll probably forget the second one by the time I get there, but let's see how this goes. Um, I would say that the most challenging part of coding is learning how to code. It can be, if you're not careful, as frustrating as learning a musical instrument, for example. A lot of people will pick up a musical instrument and want to be um, an excellent piano player or an excellent saxophone player on day one. And like learning a musical instrument, computer coding takes time. It takes practice, and you simply have to keep at it. So the first thing that's difficult or that's challenging about coding is learning. Once you've learned what to do, my answer to what's the most challenging would be when things don't work the way you want them to. And again, this can, if we go back to playing a musical instrument, we can practice and we can be good at our instrument, but when we sit down to play a new song and it doesn't play the way we want it to, or there's something that we've missed, or we've made a mistake, that can be really frustrating. And computer coding is very similar. If I'm writing a video game, or if I'm writing software for a self-driving car, and the self-driving car just goes in circles, or the video game doesn't register that the yellow bird hit the tower, it can be very frustrating. And sometimes when we're writing code, and we're writing a lot of code, it can be hard to figure out where the problem is. So the most challenging parts are learning, and then fixing any mistakes that you made, which just comes with practice. Just like playing a musical instrument, the more you do at learning and the more you do at practicing, the better you are.
And I want to flip that and then ask you, what is the most rewarding part for you with coding?
Well, I can give you the same answers in reverse, actually. So the most rewarding is when you feel like you've learned a particular coding language, and you feel confident talking about it, and you feel confident using it to solve problems. Similarly, the most rewarding thing is when what you tried to do works. And a lot of times when I'm doing examples in class with my students, we'll write too much code without testing it. And we'll just keep going with an example and we won't pay attention. And then when we test it and it finally works, we kind of all start to cheer. So it really is, it's sort of the challenges and the rewards are kind of opposites to each other. So the challenge is the learning and when things don't work, and the rewards are having learned and when things work out the way you expect them to. Those are probably the most rewarding things. This writing computer code is a lot like, again, we'll go back to the musical instrument. When you can play a song and play it without mistakes and play it the way it was meant to be played, it's a very rewarding feeling. Coding is often compared to creating art. And when we can solve a problem with computer code, and the problem that we solve is helpful to people, or is beautiful to people, or is entertaining to people, that's a really, really rewarding situation. So I'm in it for that part.
And that brings me to one of my last couple questions here. What types of other people do you find yourself collaborating with? So maybe people with other jobs or other expertise who are not coders. What other people like that would you collaborate with in the course of being a coder?
So that would depend on the job and the software that we're doing. If we're doing, I'm going to put this in quotes because not everybody's going to agree with this. If you're doing boring software, things that aren't games or websites, things that are still really important, but that we don't really classify as fun software. When you're doing software like that, often you're working with teams of other programmers. So a lot like a band, everybody sort of brings their own musical instrument and talents to the band, and coders will work the same way. I might be really good at making the turtle draw squares, but I need somebody that can make a turtle that draws circles because we're trying to do a picture of a snowman in a house. So we need somebody that can do circles and somebody that can do squares and somebody that can do triangles. It's kind of a simple example, but we do that when we're writing software. So quite often when we're writing software that isn't super fancy, we're with teams of other softwares. We usually have a boss that manages what we're doing, makes sure that we're staying on task and that we're using our time wisely. But usually it's other coders mostly. When we work on things that are a little bit different, like websites and video games, or even certain applications, a lot of times we'll work with artists. So we'll have to have background pictures, or we'll have to have characters that are drawn. Sometimes we'll work with story people, or what we would call content experts. And content is just kind of a fancy way of saying the people that tell the story. So whether or not it's a web page or a video game design, we'll work with people that do all the writing. Again, we almost always have a manager that's just making sure that we're watching our time properly. But artists and content people or story people, those are probably the most common. Sometimes we work with people that will write instructions on how to use our game or our app. So there's actually quite a wide variety of people we could work with. Right.
And we talked already about, getting started with something simple like a Lightbot or code.org with our Hour of Code, Canada Learning Code, Scratch, all of these places as places to start out and writing code, and then you can move on to other languages beyond that. Do you have any other advice for any of the students who might be watching this today who think, that seems kind of interesting, I might want to pursue that?
Yeah, you can just dive right in. My advice is to dive right in. So it depends on where you are with your reading. So again, we're not sure exactly who's watching or what level they're at. So for some kids, for some people, books may not be the best thing. There are a lot of online tutorials. So again, ask a parent, a mentor, a teacher to help you find things like that. And what you can do is you can sort of follow a video tutorial along and do it as they do it. There are a lot of books out there, so if that's a good way for you to learn, do that. I would challenge the teachers and parents to engage kids that are young and interested in coding and to code with them. Because one of the more rewarding things of working in a pair or a team is that feeling of getting it to work as a team. So definitely I would like to get teachers, parents, mentors, guardians all engaged as well. But the idea ultimately is to jump right in. Whatever you can find, whatever you can afford, whatever you have access to, just try. I can remember being about 10 or 11 at the time, and one of the books that I got from a book order form when I was in school had just programs typed in the book. It was just a book of programs that were already typed. And what I would do is I would copy those programs into my computer. And even though I hadn't invented anything, I was learning the language of computer code. And it was my very first start. So little programs that would just print hello on the screen that would take me half an hour or 45 minutes to type in. I would make mistakes. I would go back and correct them. So I really didn't accomplish anything that was sort of magnificent, but I jumped right in. I had access to the book, and I just sort of said, I'm going to try. And I highly encourage everybody out there to do the same thing. Computers are surprisingly forgiving. If you make a mistake, they really don't, they're not worried about it. Your program may not work properly, but they're not going to say anything bad to you. And so it's a fairly safe place to try something out and to make a few mistakes. But try it with your friends, try it with people you know, and see if you can jump right in with both feet and start coding.
Nice. And it seems like some of these things like Scratch, et cetera, have made it even quicker to get that reward now that you don't have to type out all those commands. You get to click and drag those commands into place and then see it all come together.
That's right. Absolutely.
Well, we've already gone over time, as I'm so sorry, I always do. But thank you very much, Aaron, for joining us today, sharing what you shared and answering our questions.
No problem. Thank you.
And information about upcoming PIR live event webinars and other Partners in Research Canada educational programming is available at pirweb.org. Happy Computer Science Education Week, everybody. We'll see you next time.